The paper of the day is The Design of a Practical System for Fault-Tolerant Virtual Machines. Authors have implemented a commercial enterprise-grade system for providing fault-tolerant virtual machines based on the approach of replicating the execution of a primary virtual machine via a backup virtual machine on another server. They have designed a complete system in VMware vSphere 4.0 that is easy to use, runs on commodity servers, and typically reduces performance of real applications by less than 10%. In addition, the data bandwidth needed to keep the primary and secondary virtual machines executing in lockstep is less than 20 megabits per second for several real applications, which allows for the possibility of implementing fault tolerance over longer distances. An easy-to-use commercial system that automatically restores redundancy after failure requires many additional components beyond replicated virtual machine execution. They have designed and implemented these extra components and addressed many practical issues in supporting virtual machines running enterprise applications. In this paper, they describe their basic design, discuss alternate design choices and a number of implementation details, and provide performance results for both micro benchmarks and real applications. Let's look at the performance evaluation. The applications that evaluate in the performance results are as follows. SPECJPB 2005 is an industry standard Java application benchmark that is very CPU and memory intensive and does very little I/O. Kernel compile is a workload that runs a compilation of the Linux kernel. This workload does some disk reads and writes and is very CPU and main memory unit intensive because of the creation and destruction of many compilation processes. Oracle SwingBench is a workload in which Oracle 11g database is driven by SwingBench OLTP workload. This workload does substantial disk and networking I/O and has 8 simultaneous database sessions. MS SQL DVD Store is a workload in which a MySQL Server 2005 database is driven by DVD Store benchmark, which has 16 simultaneous clients. In terms of network benchmarks can be quite challenging for the system for a number of reasons. First, high-speed networking can have a very high interrupt rate, which requires the logging and replaying of asynchronous events at a very high rate. Second, benchmarks that receive packets at a high rate will cause a high rate of logging traffic, since all such packets will be sent to backup via logging channel. Third, benchmarks that send packets will be subject to the output rule, which delays the sending of network packets until the appropriate acknowledgement from the backup is received. This delay will increase the measured latency to a client. This delay could also decrease network bandwidth to a client, since network protocols such as TCP may have to decrease the network transmission rate as round-trip latency increases. Let's look at the contributions of this paper. Authors have implemented fault-tolerant virtual machines using the primary backup approach on the VMware vSphere 4.0 platform, which runs fully virtualized x86 virtual machines in a highly efficient manner. Since VMware vSphere implements a complete x86 virtual machine that can run along all operating systems and applications that run on x86 platform, they are automatically able to provide fault tolerance for any x86 operating systems and applications. The base technology that allows us to read the execution of a primary and ensure the backup executes identically is known as deterministic replay. vSphere fault tolerance is based on deterministic replay but adds in the necessary extra protocols and functionality to build a complete fault-tolerant system. In addition to providing hardware fault tolerance, their system restores redundancy by automatically starting a new backup virtual machine on any available server in the local cluster. At this time, which means when the paper was written, the production versions of both deterministic replay and the VM fault tolerance support only uniprocessors VMs. Recording and playing the execution of a multiprocessor VM is still work in progress, with significant performance issues because nearly every access to shared memory can be a non-deterministic operation. Let's look at the PS score for this paper. Overall, this paper is a pretty decent read, so it gets 9 out of 10 on readability. With 10 pages long, it scores 8 out of 10 on length. It's an analysis of an existing system with pretty good description, so that makes it 9 out of 10. Its industry value and learning meter is high, so it gets 9 out of 10 on each, with overall PS score of 9 out of 10.